Good afternoon. Thank you, Mr. Chairman. So, ladies and gentlemen, good afternoon. Thank you for the word. I would like to present here our first result about the tensile properties of FRP bars under effect of elevated temperatures. So, in our project and in our research, we focused on a behavior of structures reinforced with FRP reinforcement. In our project, we suppose that we will use the FRP reinforcement, which is used as an internal reinforcement. And where it's possible to use these reinforcing bars, we may use it for the reinforcing of new structures, or we may use it for the restoration of old or damaged structures. The main characteristic of these bars is a combination of two materials, basically the fibers, which are from glass, carbon, basalt, or aramid material, and these fibers are combined with the matrix or a resin. The next basic characteristic is that this material is linearly elastic until the failure without any yield strength. Advantages of this material is namely the high tensile strength, which is much more 2 times or 3 times higher if we use the glass fibers, and practically 6 times higher if you will use the carbon fibers. Also, it's a non-conductive material, has a chemical resistance, is very lightweight. Also, this material has a disadvantage, is namely the low strength across the fibers, so the low shear strength and the low value of the Young modulus. So in our experiments, we focused on a behavior of these FRP reinforcing bars under effect of the elevated temperature or under effect of a fire on some structure which is reinforced with the FRP bars. So we want to obtain the information about the behavior during the increasing of the temperature. We start with the first phase last year and this year. So we started testing of GFRP bars, so the bars reinforced with the glass fibers. And we use 2 types of bars with the same type of the fibers, but with the different metrics and different surface preparation. The first material, a bar, is produced in the Czech Republic. It's a glass fiber reinforcement with the surface which is coated by a sand. And the second type of the bars is the bars which are produced in Germany. And the surface is prepared with the ribs to obtain some anchorage between the concrete and the reinforcing bars. But at the beginning, we focused only on the behavior of the self bars under effect of elevated temperature. As you can see here, the strength of this material is more than 900 megapascals, but the modulus of elasticity is from 50 to 60 gigapascals only. So this value is much more lower than classical steel reinforcement. We use 2 testing procedures. The first procedure is using of electric high temperature chamber. So on a picture, you may see the chamber in the loading frame. We are possible use the temperature up to 300 degrees in this chamber. And for the testing, we use the steady state temperature conditions. So it means that in the first step, we apply the temperature, and in a second step, we apply the loading on reinforcing bars. The second possibility how to test the reinforcing bars is use of the small gas testing furnace. We built this furnace on a faculty, so we are able to use this furnace for the temperatures up to 1200 degrees. And also we are able to load the bars, but not only the reinforcing bars, but also the concrete or other type of the structures according to temperature curves. For this type of the structure or for this testing procedure, we use the transient temperature conditions. So this means that in the first step, we will apply the loading, and in a second step, we will apply the increase of the temperature. So why we use these two procedures? As I said, we got two test procedures. The first one is an electric chamber, and the second one is the gas furnace. We use electric chamber namely for high stress levels and gas furnace for low stress levels. But why? It's namely because of the creep behavior of FRP reinforcement. We know that if the FRP reinforcement is stressed on a load level which is higher than 60% of a strength, the creep will start in a reinforcing FRP bars, and it has influence and influence of the creep will increase with the higher level of the stress in a reinforcing bars. Therefore, we suppose is for the high stress levels, it's better to use the electric chamber in which we first apply the temperature, then we apply the loading, so we will prevent the influence of the creep. And for the lower stress levels, we use the gas furnace. In this furnace, we first apply the loading and then we apply the temperature. And of course, the stabilization of the stresses in a reinforcing bars will take some time, more than 15 minutes sometimes. So the negative effect of the creep is not used here because we use only lower stress levels, lower than 60% of the strength. But also we may get the assumption that for the higher load levels, we may suppose that reinforcement will fail at lower temperatures. Therefore, we use the electric chamber for low temperatures up to 300 degrees, and gas furnace is used for the high temperatures up to 900 degrees Celsius. Now I want to describe the experiment procedure. So the first one is electric chamber. So again, you may see here the electric chamber in the middle of the loading frame. The bars are held in a cold area here at the top and at the bottom. And of course, the first step is rod installation. Then we start with the temperature increasing in a chamber, and we hold the constant temperature in the chamber according to the required level of a temperature. After the stabilization of the temperature in the chamber, we start with the loading of the bar. It will take approximately from 4 to 6 minutes to rupture the bar. And on the right picture, you may see the rupturing of the bar in the chamber. The advantages of this procedure is, of course, that we obtain the uniform temperature distribution because we may hold the temperature around the bar for some times before we apply the loading. And the next advantage is for high stress levels, we are able obtain the results, the clear results, without negative effect of a creep on a reinforcement, because loading will take only 5 minutes, for example. The main disadvantages is namely that this procedure does not correspond to real behavior of a structure, because we first apply the temperature, then we apply the loading. And the next disadvantages of this chamber is that the maximum temperature which is possible to use inside is 300 degrees of Celsius. The second method is using of gas furnace. So as I said, we build this furnace. So you may see the black furnace in the middle of this picture, and around this picture we build this loading frame. So again, the first step is installation of the bar, and then we start with the loading of this bar. After the stabilization of the strain of the reinforcement and stabilization of the stresses inside of the reinforcing bar, we start with the fire test. So we are able to increase the temperature according to the nominal 5 curve, according to standards. And also we are able to hold the constant tensile force during the whole fire test. And again, after the bar failure, we finish the experiments. In these cases, we use namely the lower stress levels. I got here some pictures from this experiment. So on the left side, you may see the bar installation. So we got here the fixed end into the separate frame. So this separate frame is around the furnace, and on the right picture, you may observe the loaded end. After the installation of the reinforcing bar, we start with the installation of the thermocouples. So we got here 4 thermocouples inside of the furnace to monitor the temperature in the furnace, and 5 thermocouples is installed on a surface of a reinforcing bar to obtain the uh, thermal field along the reinforcing bars. In the next step, we apply the protection thermal insulation against the direct flame because we want to observe the behavior of the reinforcing bar inside of the concrete structure. So we want to prevent the direct flame influence on a surface of the reinforcing bars. So therefore, the whole bar is coated by this thermal insulation. And then we apply the loading. So here we got the hydraulic jack and the load cell, and we monitor the applied force during the whole experiment. So before we start the fire tests, we wait for the stabilization of the force. We wait for the stabilization of the stress in a reinforcement and the strain in a reinforcing bar. And in the last step, of course, we apply the temperature. We start with the fire test. So we apply the influence of the increased temperature according fire curve. In our case, we use the nominal curve ISO 834. Advantages of this type of procedure is namely that it corresponds to the real behavior of a structure exposed to the fire, because in the first step we apply the loading and then we apply the influence of the fire. So it's the same procedure like the fire scenario in a real structure. And the next advantage is that in this furnace we are able to increase the temperature according to 5 curves. The main disadvantages is that, namely for higher stress levels, we obtain the non-uniform temperature distribution along the cross-section. But if we will use this furnace only for the lower stress level, to rupture this bar will take more than 30 minutes. So during these 30 minutes, we will obtain practically constant temperature along the bar. And as I said, it's suitable namely for lower stress levels because it took from 10 to 15 minutes when the experiment starts. And if we will use this experiment for the higher stress levels, then the effect of the creep will get the negative effect on results. And because we want a clear results and we want to obtain only influence of the increased temperature, therefore we use this procedure only for the stresses up to 60% of the tensile strength. Now, something about the results. So I divide the results to 4 groups. In the first group, up to 200 degrees of Celsius, you may observe that the shape of the reinforcing bar and the color of the racing bar is practically the same. And you may observe the classical rupturing of the FRP bars along the fibers. This is typical type of the failure under the normal temperature. So up to 200 degrees, we are slightly above TG. So TG is a glass transition temperature for the matrix. So we may suppose that the softening of the matrix start. And as I said, the failure is standard as at a normal temperature. And this type of the failure is typical for the load level greater than 70% of a tensile strength. From 200 to 300 degrees of Celsius, the behavior will slightly change, and you may observe the change of the color, namely the change of the color of the matrix. The matrix now is very close to self-ignition. The melting of the matrix continue during the increasing of the temperature, and the chemical change start in a matrix. Load level is approximately from 50 to 70% of the tensile strength. Over the 300 degrees of Celsius, approximately to 500 degrees of Celsius, the behavior again change. You may see the reinforcing bars after the end of the experiments in this range of the temperatures. You may observe that the bars are now black. It's namely because of self-ignition of the matrix. In this case, the whole matrix burn, but it's not the burning of the matrix from a direct flame. it's a self-ignition only from increased temperature. So when the temperature is greater than 400 degrees approximately, the matrix burn itself. And low level is now approximately from 40 to 50% of tensile strength. The last stage is for the temperatures greater than 500 degrees. We may observe that the color again is changed. Now we got here only white color because only glass fibers remain in a cross section and the whole matrix burn out from a cross section. So now we got here only the bearing capacity of fibers. But even for these temperatures, up to 500 degrees, the bars, only glass fibers, are able to carry the loading to the load level up to 40% of the tensile strength. I got also the diagrams which show us the results of our experiment. So on the left side, we got the results from an electric chamber. We may observe that the maximum temperature here is 300 degrees, and we use it for the load levels greater than 50% of the tensile strength. So we obtain the first part of the results, and we suppose that these results are without influence of the creep, as I said, because we first applied the temperature and then we applied the loading. The second part of the results is from a gas furnace. So we start at the load level 60% and we going down to approximately 15%. If we combine these results together, we obtain the final curve, so which gives us the behavior of the FRP. In this case, FRP from with glass fibers. So the first area is the melting of the matrix, then burning of the matrix, and at the end of the line, you may observe the results for the only glass fibers. I also got here this gray line. So this is assumption about the behavior of FRP reinforcing from Professor Safi. So he supposed that the maximum temperature which is possible to use for the design is only 400 degrees. But if we will suppose that this line, the green dashed line, I call it, it's a long-term design stress of the reinforcement, which is maximally 30%, according to most of the standards, is 30% or below. So maybe we may use the temperatures up to 700 degrees for the design of the reinforcing bars. But as I said, we got here some other problems. So as I said, long-term design strength is usually below 30%. Therefore, we may maybe use 700 degrees as a temperature which is possible to use. But on the other hand, we got here other problems. The first problem is anchorage of the reinforcing bars. We may also suppose that the high temperature will have a negative effect on a behavior in anchorage zone, because if the anchorage zone is calculated from a bond between the matrix and the concrete, and the matrix will start melting above the temperatures from 200 to 300 degrees, then we must somehow anchor the reinforcing bars in a cold zone to prevent the failure in an anchorage zone. Because then if you want to use for the calculation, for example, 400 degrees or 500 degrees as a design temperature or a critical temperature for the design of the structure, if the reinforcing bar will fail in a bond area or in an anchorage area, then the structure will not be sufficient. And the second assumption is about the usage of the structure after the fire scenario. Of course, we may calculate with 700 degrees as a critical temperature, because from the previous diagram, we know that the load level is under the 30%. But what will be with the structure after the fire scenario? Because if the temperature will be greater than 500 degrees, then the matrix will burn out from a cross section, and only fibers will remain. So We must focus not only on a behavior of the bars, but also we must focus on a behavior of different type of the fibers. So in the next part of the experiment, we will continue with the basalt fibers, and also we will focus on a behavior in an anchorage zone under elevated temperatures. So it's the next part of the experiments, which is prepared for this summer and for the next year. So thank you for the attention. That's all from our experiments. So it was very nice. Give me the time here on this conference. Thank you.